Right, today we're going to do a problem where I have a yo-yo and it's attached to the ceiling and I'm going to let it fall. And I want to know what's the acceleration of that yo-yo. Now you can imagine that if I dropped it, the acceleration would be g. But because there is some tension holding that yo-yo up, its acceleration's not going to be g. It's going to be a little less. And so I want to figure out what is that acceleration as that yo-yo falls. Okay. So we have two options available to us. One of them, we're going to be using an I value for the moment of inertia through the center. Okay? This is just because maybe you don't know how to use the parallel axis theorem. Okay? So this method, there is one assumption we do have to make, uses both the linear and the rotational directions. Option 2 just uses rotation, but we do have to use the parallel axis theorem. So I'll walk you through both those methods. So option 1, we're going to set up our linear problem. Now, because we're doing a linear and rotational, and they're going to have some common terms, namely tension, and we also want acceleration to be common, we're going to choose our acceleration for this as down and make that our positive direction. So here I have mg minus tension equals ma, and that's the acceleration of my object, or my center of mass. Over here in the rotational situation, okay, so I have tension acting perpendicular to the radius, so I have tension times r is equal to I. And our yo-yo is essentially a disk, so I'm going to use 1/2 mr squared. And again, I can just get that off of my table, or it will be given on an AP test. And alpha, we're going to go ahead and make a substitution here and say that alpha is the linear acceleration at a point on the edge. Now, you might say, well, this was the center of mass acceleration, but this is the acceleration of a point on the edge, or the string, essentially. And so what we can do is we can say that the problem's going to be the same. Now, this is a reference frame question, in that I could do this problem as the yo-yo falling down, or I could do this as not the yo-yo falling down, but the string moving up. And so the acceleration of the string upward is going to be equal and opposite to the acceleration of the center of mass down. So I can either look from the center of mass frame and say, no, the string is accelerating up, or I can look from the string's frame and say the acceleration of the center of mass is down. Both frames of reference are equivalent. So what I can say then is they are opposite and equal. All right, so these accelerations are equivalent, and I have them here both as positive. We like to make this substitution for alpha because then we get our r's to cancel. Now, we were lucky here in that our string was wrapped around the outside edge of our yo-yo. Now, if it's not wrapped around the outside edge, these r's aren't going to cancel because that string is not going to be attached at the radius of the object. So these r's are the same, but this r would be different. Okay. So now I end up with something that says the tension is equal to 1/2 ma. We can now substitute that in over here. So I have mg minus 1/2 ma equals ma. We get an m to cancel. We got a negative 1/2 a over here. We're going to go ahead and move that over the other side. So 1/2 a plus a gives me 3/2 a equals g. And so the acceleration is 2/3 g, okay, which is less than g, which we suspected. So this way you do have to make that assumption and make that link there between the two frames of reference. The next method, you don't have to make that leap of faith on the reference frame. You can get away with just thinking about the parallel axis theorem. So let's try that one. Okay, so option 2, now I can think about not so much it rotating about the center, but it rotating about a point here. Okay? So this you can imagine if I took my wheel and I just let it fall from this point. Okay? You see how it's going to rotate. Right? And so I can then say that the rotational acceleration of this point, alpha, rotating this way, is going to also be the linear acceleration of that point. Okay. So I set this up. So here is my axis of rotation. So my torque is actually mg times its distance from the axis of rotation, and mg acts at the center of mass, so it's a distance r away, is equal to I Ooh, but we're going to have to figure out the I, because we don't have that on our chart. So we're going to use the parallel axis theorem. So the center of mass rotation, or moment of inertia, is 1/2 mr squared. Okay? Plus mass times the distance from my new axis of rotation to my old axis of rotation, which is r. So I have r squared here. And so you see I have 1/2 mr squared plus mr squared, so I is equal to 3/2 mr squared. We're then going to plug that in for I, so I have 3/2 mr squared. Alpha, I again want to make that substitution. Again, this is going to be my center of mass acceleration because we're talking about the linear acceleration of this point, which is my center of mass, divided by r. Again, we make that substitution of alpha because our hope is that our r's are all going to cancel. In this case, our m's also cancel. And so all of that gets down to g equals 3/2 a. And so a equals 2/3 g. So whichever method you find more useful, go ahead and use. Okay.